Hey guys, in this video we're going to go ahead and we're going to talk about something called the fundamental theorem of line integrals. But before I actually state the fundamental theorem of line integrals and we go through an example where we try to use the fundamental theorem of line integrals, what I'd like to do is kind of give a little bit of the rationale behind where this idea is going to come from. All right. So what I want us to consider is, let's consider that we're existing in some sort of a vector field, right? And let's say perhaps we want to move a particle from, let's just say, point A up to point B. Right? So there's many different ways that we can get from this point A up to this point B. We could say, oh, well, we could just take the straight line approach and move directly from A to B. Or if we wanted to take some other approach, we could say something like, maybe I want to climb straight up this way and then head straight over, maybe straight over and slightly down to B, or maybe we want to take kind of a curvy approach from A up to B. So these are three different paths that we could take from A to B. Let's call them C1, C2, and C3. Okay. So here's what I want us to consider, right? If we're really thinking about maybe moving something between 2 points, let's think about it in like a real world scenario. Let's pretend we want to carry some sort of an object up a hill, okay? So pretend that this is us hanging out down here. Maybe we want to carry a bowling ball up this hill and take it to point B, take it up to the top of the hill and roll it down and have a little bit of fun with it, right? Well, we know that the vector field that we're going to be living in probably going to be influenced by gravity. That's a pretty natural feeling vector field that we could live in. And if we wanted to draw a couple of vectors in our vector field, we could assume that they're all pointing us downwards, or all pointing downwards. And they all have roughly the same length. We're going to assume that point A isn't too far away from point B, such that it would cause a change in the gravity or the direction of the vector field. So if we have this type of a situation going on, from physics, we know that regardless of which one of these paths we take from A to B, it's going to require the same amount of energy. In other words, if we start right here at point A and we begin carrying the ball, let's pretend it's a ball, up along this curve C2, well, we know that what we're doing is we are converting the energy in that ball into potential energy, right? We're kind of raising its elevation. Right? We're not going to consider changing its velocity. We're just going to consider it at each fixed point in time, right? But if we were to go ahead and we were to take that maybe down along the second path, well, down along that first half, we'd probably be giving the ball some sort of velocity. So we're changing potential energy into kinetic energy. So down here, we might say that that corresponds like a height of 0. So we could think about down in this valley, we have a potential energy of 0, but we might have some high kinetic energy, and then it will require that kinetic energy that we have, plus we're going to have to walk it up the hill a little bit. I'll get to point B eventually. So that's going to require the same amount of work to get from point A to point B along that second path. And the same thing kind of along this third path, right? What we're going to do is we're going to require a lot of energy in order to convert the energy in the ball to straight, potential energy, because once we get it to the top of the hill, it's not necessarily moving, but then it's going to convert some of that into kinetic energy as it starts to roll down to B. So regardless of which path we take, we're going to use the same amount of energy to get that ball from point A to point B. And these are really only 3 paths. We could talk about infinitely many different paths from point A to point B. So what I'm trying to get at here is that if we wanted to start thinking about the work required to get our ball from point A to point B, it's really entirely independent of the path which we choose to take. And the reason that it's entirely independent of the path we choose to take is because that field that we're living in, the gravity field or the force field, was a conservative force field. Right? And this is what leads us into our fundamental theorem of line integrals. So our fundamental theorem of line integrals states, if we have some sort of a conservative vector field, This can be extended in 3 dimensions also. It's pretty easy to see how it extends into 3 dimensions. But if we have a conservative vector field, then the line integral over the curve C which is going to be given by a vector valued function, r of t equals x of ti minus y of tj for values of t, let's say between a and b, is given by right? So we're going to have the integral over our curve of our vector field, f, dotted with dr. And we know that we could also write this as the integral over our curve of n dx plus n dy. Well, this is going to be equal to a lowercase f of x, y, evaluated from t equals a to t equals b. But if you remember what x and y are, well, our x coordinates and our y coordinates both come from our curve. So the x coordinate is really a function of t, and the y coordinate is really a function of t. Let me go ahead and make this a plus sign. That didn't need to be a minus sign. I don't know if I said plus or minus back when I was writing it down. So what we're going to have is we're just going to have f of x and y, but we're going to have f of x of t and y of t. Okay. So this is just going to behave exactly the same way as a definite integral from Calc 1 would behave, where here we're going to have lowercase f of x of b, y of b, minus f of x of a, y of a. All right. So the big question now should really be, what is this lowercase f function? We talked about capital F, that was our vector field, but lowercase f is really our potential function, right? So since our vector field was conservative, we know that there's going to exist some sort of a potential function. So that means the gradient of f is equal to capital F. In other words, we can say that lowercase f is the potential function of capital F. All right, so let's go ahead and let's play with an example where we actually evaluate a line integral using the fundamental theorem of line integrals. So we'll go ahead and we'll evaluate the line integral over a curve C of f dot dr where C is a smooth curve from the point -1, 4 to the point 1, 2. And f is 2xyi plus x squared minus yj. Okay, so here's the thing. In general, this would not be a problem that we would be able to answer, right? Because we don't necessarily know what our curve is. Okay, so we have our curve, and all that we know about our curve is it passes through 2 points, the point -1, 4 and the point 1, 2. So if we wanted to think about this, well, we really have this type of a situation. Here's our point -1, 4, and then we're going up to the point 1, 2. So think of all of the curves that pass through those 2 points. We might have a straight line passing through those points. We might have something that looks parabolic. We might have something else going through those 2 points. Heck, we don't even need our curve to go directly from that point over to the other point. We could have our curve kind of spiral all around. Just as long as it starts at the point -1, 4 and ends at the point 1, 2, we're good to go, right? Depending on which one of those curves are, that could change the value of the integral, is what I mean to say. Now, the thing is that if we are living in a conservative vector field, though, it's going to be entirely independent of which one of those paths that we choose. So the value of this line integral will not depend at all on which one of these 3 or 4 paths that I drew there for you. So let's go ahead and let's check and see if our vector field is conservative. That'll be the first question that we want to ask, because if yes, then we can use the fundamental theorem of line integrals. So we'll ask ourselves, not if, is f conservative? So remember, in order for us to determine whether or not a vector field is conservative, we need to consider the I component and the y component, or the I component and the j component, I should say. And we want to take their partial derivatives with respect to the opposite variables. So we're going to check, is the partial derivative of 2xy with respect to y, is that going to be equal to the partial derivative of x squared minus y with respect to x? So we'll go ahead and do it. If we take the partial derivative of 2xy with respect to y, treat y like a constant, x is a variable, we're left with a 2x. Take the partial derivative of x squared minus y with respect to x, we're treating x like a variable, y like a constant, we're left with a 2x. So since 2x is in fact equal to 2x, we're good to go. So f is in fact a conservative vector field. So since f is conservative, that means we can use the fundamental theorem of line integrals. Okay. So remember what our fundamental theorem of line integral says. It says that the integral over a curve C of f dot dr is just going to be f of x of b, y of b, minus f of x of a, y of a. But here we can kind of go back and we can kind of interpret what these x coordinates and y coordinates are. Because we have this curve, let me go ahead and clean this up a little bit. We have some sort of a curve C that's going from the point -1, 4 to the point 1, 2. So we can consider -1, 4 to be some x of a, y of a, and we can consider the point 1, 2 to be some point x of b, y of b. Make this look a little more like an A up here. Right? So we've got the x of b, we've got the y of b, or sorry, x of a, y of a, x of b, y of b figured out. The last thing we need to do is we need to find this lowercase f function. So that means we need to find our potential function. So remember how we find our potential function. Right? So our potential function f of x, y is going to be equal to, well, it's going to be the integral of the I component of our vector field with respect to x. So it's going to be equal to the integral of 2xy with respect to x. And if we evaluate this integral, what we're going to be left with is we're going to be left with a x squared y. But we also need to remember where that 2xy came from. It came from taking the partial derivative of lowercase f with respect to x. So any function of y is going to entirely vanish. So our constant of integration should be some arbitrary function of y, right? Now, to get back to our potential function, it's also going to be the integral of the j component with respect to y. And our j component is this x squared minus y. So if we integrate x squared with respect to y, we get x squared y. And if we integrate y with respect to y, we get a y squared on 2. And remember where the y component of our vector field came from. It was the partial derivative of our potential function with respect to y. So any function of x would vanish. So we need to include an arbitrary function of x here, right? So these two expressions that I have written on the page have to be equal. So what that means is that f of xy has to be equal to, well, each of these have an x squared y in them. Now, the top one has plus some arbitrary function g of y, while our bottom one has this negative y squared over 2. So we're good to go there. And then h of x, well, h of x, I guess at this point would really have to be a constant, but since we're evaluating a definite integral, we don't need to worry about any constants that arise from our integrals, as they're just going to cancel when we plug them in. So what we have here is we have a potential function. So now we can go ahead and we can finally go back to the integral which we're trying to evaluate, right? So the integral that we were trying to evaluate, let me scroll out a little bit just so I can see all of it, was the integral over our curve C of f dot dr. And we know that this is going to be equal to lowercase f of x of a, or sorry, x of b, y of b. Well, that was the point 1, 2, minus f of x of a, y of a, which was the point -1, 4. So we'll go ahead and we'll plug in 1, 2. That's going to give us 1 squared times 2 minus 2 squared over 2, which is just 2, minus, we'll plug in -1, 4. Well, that's going to give me a -1 squared times 4 minus a 4 squared over 2. 4 squared is 16, divided by 2 is 8. So what are we left with? Well, we're left with a 2 minus 2 is 0, and then we're left with a minus 4 minus 8, which is a -4. So we're just left with the value of +4. And there we've used the fundamental theorem of line integrals to evaluate a line integral. Pretty nifty, right? There's one other big idea that I want to talk about in this section, and it's a pretty simple idea. It's the idea that if we're integrating over a closed loop or some sort of a closed path in a vector field, in a conservative vector field, well, the value of the line integral is just going to end up being 0. So if we have a conservative vector field and C, given by some R of t, is a closed loop, or a closed path, then the integral over the curve of f dot dr is just going to be equal to 0. And you can kind of see why that's going to be, because if we're talking about integrating over a closed loop, so say we have a conservative vector field, I'll draw a couple of vectors in here. Maybe we're thinking about our downwards force vectors also, our downwards force vectors. And we want to move a particle along some closed loop. So we'll let this correspond to t equals a, we come all the way back around, and we'll let that same point correspond to t equals b. So if we're thinking about work, the total work required to move a particle from a point back to itself just ends up being 0. The total energy expended is 0. All right, so that's really what this statement here is saying. It's saying that if you're in a conservative vector field, the line integral over a closed loop is always going to be 0. So if you end up where you start with, it's basically saying you didn't do anything at all. Okay. Now, there's one last little set of statements that I'd like to make, but we're really not going to do a whole lot with them at this point, and most of them are going to feel pretty trivial, but I would like to at least have them in your notes. So if we let f of xy be some sort of a conservative vector field, which you can write as like an mi plus nj, or we could also do this in space. So we could also have a conservative vector field in space. Sorry, at this point it's just a vector field, not a conservative vector field. So we have a vector field. Then the following are going to be continuous. Or sorry, the following are going to be equivalent. Sorry, let's go ahead and introduce a curve C also. All right, so the first one is going to be, assume that we have f being conservative. All right, so we really can't, we're really not saying anything now. All that we have is we have a vector field, and if it's conservative, then what I'm about to say are all going to be equivalent. If f is not conservative, then none of what I'm about to say are going to be true. So 2. The integral over that curve C of f dot dr is independent of path. Meaning you can pick and choose any path that you would like to evaluate this integral from where t equals a up to t equals b, and you're going to get the same exact value. And basically this is just a fancy way of saying the fundamental theorem of line integrals is applied. And then the last condition is that the integral over the curve C of f dot dr is equal to 0 for every closed curve C in R. All right. So what I mean by that is that if you have some sort of a vector field, and you evaluate a line integral over every single closed curve. This is a difficult thing to do because there's infinitely many closed curves. And you get 0 for each and every one of those, well then these other two conditions are also going to be true. So this is one way to show that you have a conservative vector field. Granted, it's a very difficult way to show that you have a conservative vector field, but you could do it potentially. So with that, I think I'm going to go ahead and leave this video here. We'll pick up with this idea a little bit more starting on Friday. So have a good one, guys, and I will catch you then. Thank you.